Welcome back from the ad break. Yes, you're still sitting with me, Utobi Lenkosi, and we are doing Physical Sciences Grade 12, paper number 2 revision, which you write tomorrow. Just another big shout out and tons of love coming from us to Liberty. Thank you so much for sponsoring the show. Truly, none of this would be happening without you guys. So right before the ad break, I showed you how we answer Le Chatelier's principle with calculations, how to reason, and how to tackle all those questions. So now in this segment, what we're going to do, we're answering another question on paper number 2. Thank you so much for all the questions that came through. Remember, if you haven't done it yet, please do download the Tenfold education app, and you can send through any questions, so all our teachers can actually help you during your preparation time. So without wasting any time, let's answer this next question. So this was question number 6, and it was from Leah Mlunui. So we have dinitrogen tetraoxide, and it's given to us, decomposes to nitrogen dioxide. Already you can see the trend. The previous question also said decomposes. Decomposition is a type of reaction, and we have certain things that happen or are given off. So we have NO2 gas, which is sealed in a syringe. We have a volume of 2 cubic decimeters. I love the volume because we don't have to convert it. Remember, if your volume is given to you in cubic centimeters, you must divide that by 1,000 to get it to cubic decimeters. So I can see my syringe here. The question continues to say the mixture reaches equilibrium at a temperature of 325 degrees Celsius according to the balanced equation. So I can see it's colorless on the side and it's then brown on the other side. Now I just want to take us back a little bit. There's a question that we already did where we were talking about bromine water and stuff like that. Will it be colorless? Would it change? And so forth. So already you can see the trend on what they do. There is a certain color. It is then colorless. Now remember, if the equilibrium shifts in such a manner, it will then favor the colorless or will then favor the brown side of the reaction. So already keep that in mind. So on the left-hand side, it is colorless, the reverse reaction. The forward reaction is then brown. The question continues to say, when equilibrium is reached, it is observed that the color of the gas in the syringe is then a brown. Aha, I see that on the right-hand side, it is then brown. 6.1 says you must state Le Chatelier's principle. Now, in chemistry, Le Chatelier is as important as Newton's first, second, third, and Newton's law of gravity is in paper number 2. You must know Le Chatelier's principle off by heart. So without wasting any time, for 2 marks, let's state Le Chatelier's principle. Remember, like I always say, you cannot fail because you were lazy to read. Le Chatelier's principle is quite a long one, so you do need to practice. Remember, no slang allowed. So Le Chatelier's principle. Le Chatelier's principle. There we are. And this is what Le Chatelier's principle says. He says, when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium. It will do so by favoring the reaction let's just spell this right, favoring the reaction that will cancel or oppose, not change, oppose the disturbance. You must know this off by heart. I just want to read this over and tell you guys where most of you guys make mistakes. When the equilibrium in a closed system is disturbed, the equilibrium will reinstate. The equilibrium does not move, right? It can shift, but it doesn't move. It reinstates in a new equilibrium by favoring the reaction that will not change. We can say cancel or oppose the disturbance. That is what Le Chatelier's principle says. Let's look at 6.2. 6.2 says, the syringe is now dipped into a beaker of ice water. Now you must think, aha, we are decreasing the temperature. The temperature was 325 degrees Celsius. In ice, water temperature is then decreased. After a while, the brown color disappears. Now, already you can think. When we had the brown color, we were favoring the forward reaction. That is why it was brown. The brown color in ice water disappears, which means that it is going to then favor the reverse reaction. Lowering temperature causes the equilibrium to shift in such a manner as to favor the exothermic reaction, right? So now let's see what the question says. That is the theory that I know. In ice water, we are decreasing the temperature. If the brown color disappears, it means that we are favoring the other side. Let's see what the question says. Is the forward reaction exothermic or endothermic? Explain using Le Chatelier's principle. Already I can see that the forward reaction will be endothermic. We must explain using Le Chatelier's principle. I'm going to show you how we're going to do that. Let me work here on the side. It's fine. So 6.2, it is endothermic. Because lowering temperature will cause the equilibrium to shift in such a manner as to favor the exothermic reaction. Now we must explain, right? I do like writing it in bullet form, but if you do prefer writing it as a paragraph, you're more than welcome. So if you decrease in temperature, and it is for 3 marks, so you need 3 points. Decrease in temperature favors the exothermic reaction. It favors the exothermic reaction. Another point, we can say that the reverse reaction is favored. That the reverse reaction is favored. Why do I say that? Just want to go back to the question. If the forward reaction was the brown gas, then it favors the colorless, right? That's why the reverse reaction is then favored. Another point we can say is that the number of moles, remember when you talk Kc and equilibrium and stuff, we talk moles, the number of moles of N2O4 gas will increases. The number of moles, we have the number of moles of NO2 gas decrease. According to Le Chatelier, that is then what will happen. So this was for 3 marks. So you get a mark for saying exothermic or endothermic, and then you get a mark for actually giving your different points. Now remember, I would always say give as many points as you can. Now already you can see we had ice water. In the back of your mind, you need to know what the theory then says about an increase in temperature. The examiner is trying to confuse you by just saying ice water, but you know ice water means we are decreasing the temperature. Remember, if there is a change in temperature, it will either favor one or either of the sides, depending on what the reaction is. In this case, we're told that it was brown, and then all of a sudden, the brown then disappears. So that's where your points need to actually come from. So let's look at the next one. Number 6.3 says, the volume of the syringe is now decreased. So the volume gets smaller, so we're increasing the pressure while the temperature is then kept constant. What they want us to do now, how will each of the following be affected? Choose from increases, decreases, or remains the same. Now guys, something that you must always remember, put in the back of your mind. If you have a container and you have particles and you can actually move them and shake them around and so forth, if you decrease the volume by increasing the pressure, you are actually changing the spaces between the particles. In grade 10 and grade 11, we do what we call the kinetic, or we learn about the kinetic molecular theory. What happens to the spaces, what happens to the kinetic energy, and so forth. Now, talking about Le Chatelier's principle is that when we do this, it actually affects the rate of a reaction positively, or it will affect the rate of a reaction negatively. So now in this question, they're asking us, what will happen? Will it increase, decrease, or remains the same? If ever you're reading a question like this, try to think about it practically and see what happens. So let's see what we're going to do with these ones. We have decreased the volume while the temperature is kept constant, so the kinetic energy of the particles remains the same. How will each of the following be affected, right? The number of moles of N2O4. So let's see, I've got my N2O4, it is my reactants, right? We have made the space a little bit smaller, so it means that it will then increase because of more effective collision. There's less space between the particles. So let's just start here. This will be 6.3.1. I am doing 6.3. It will increase. We have decreased the space between them, meaning that more effective collision. I'm bringing in a little bit of the kinetic molecular theory. The more effective collision will actually take place. Then again, we have decreased the volume while the temperature is kept constant. What will happen to the value of the equilibrium constant? Now, something that you must remember about the Kc. The Kc can only be changed by a change in temperature. So changing the volume, whether big or small, and changing the spacing between the particles does not change the Kc. When we increase or decrease the volume and the concentration and so forth, that affects the rate of a reaction. However, Kc is only changed or altered by a change in temperature. In this case, what did they say? They said temperature is kept constant. So the value of the equilibrium constant does not change in any way. It doesn't increase, doesn't decrease. However, it remains the same. If you had to give an explanation or a reason for this, let me just write remains the same. It remains the same. It remains the same. Only a change in temperature can change the Kc. So we're going to do 6.3.3. Let's look at the last one for this section. The next one says, how will the rate of the forward and the reverse reaction be altered? Remember, we have decreased the space between the particles. It means that it will increase, more effective collision will then take place because they have more space, they have less space, and they will collide more often. So it will increase. If you decrease the volume by increasing the pressure, you increase the rate of a reaction because the particles don't have so much space to actually move around in. Here we've got another calculation for Kc. So the previous one we had 7 marks. This one is for 8 marks. So we are told initially 8 moles of N2O4 is placed in a syringe with a volume of 2 cubic decimeters. When equilibrium was reached, it is found that 20% of N2O4 had decomposed. Now, percentage form. If you have 20%, always think of percentage at 100. If I give you 20% of something, how much do I have left? I've got 80%, because 80% plus 20 gives me 100. I have a whole thing. I only give you 20%. Whatever's left is then 80%. Always think of percentage like that. 20% of N2O4 had decomposed. If the equilibrium constant Kc for the equilibrium is 0.16, it is reached at a temperature of 3 to 5 degrees Celsius, we must calculate the value of X. Then again, some teachers use the ICU, I use the initial, used, and equilibrium. Doesn't matter which one you use. You can use the table, you can use the ratios, whatever method you choose, always show the examiner how you got to that answer. That's all that you need. They're looking for certain parts, certain variables, and that's where you get a mark for. I'm going to do my method. I'm going to show you how I'm going to work this one out. First things first, you always write the equation at hand. So this is number 6.4. I am told I have N2O4, and on this side I've got 2NO2. I'm told that it is in a volume of 2 cubic decimeter, dm3. I know that the Kc for this is given as 0.16. Remember, if you already are given your Kc, there's one unknown that you need to find. The way I do it, I say initial, I say used, I say equilibrium. It is a mole ratio of 1:2. On top of the used, I write 1 mole. On top of this one, I'm going to have 2 moles. Initially, these are your reactants, these are your products. Initially, you don't have reactants, right? However, you are going to use your reactants. It's going to be a minus because they're going to be used. On this side, you are going to make your products, right? I'm going to work on the side just to get percentage form. I am told, let me just read this part, this section again, that 20% of the N2O4 had then decomposed. I'm going to show the examiner how I'm going to get my answer. Remember, if you've got 20% of something, remember, think of mathematics. It means you have 20 over 100, right? Let's see what value that is. So I'm going to say 20 over 100. Therefore, I get 0.2. So this means I'm going to have 0.2 moles. I'm going to have 0.2 moles. Now, I'm just going to add on to that to say, if you've got 0.2 moles, it means that 80 of that was actually left over, because 80 plus 20 gives me 100 over 100, and that will then give me a 1. They said 20% decomposed, 20% will be 0.2. That is where I get my 0.2 from. So at the used, I'm going to have my 0.2, and on this side I've got 2 moles, but it's a mole ratio of 2, so I'm going to have 0.4. If 1 mole is 0.2, remember they said x, so it will be 2x. I don't know what x is, but I know that 20% of whatever x was actually decomposed. If 1 mole is 0.2, it's a mole ratio of 1:2, so 2 moles will then be 0.4, right? If you had nothing at the beginning, all of a sudden you've used 0.4, it means that you must then also use 0.4 moles on this side. Now, I'm going to continue to say on this side, I've got 0.2, but at equilibrium, I must have 0.8 because only 0.2% decomposed, which means 80% is what is left at equilibrium. Now, I'm going to find what the value of 80% is over 100. I'm going to have 80 over 100 over here. I'm going to get 0.8. So this will give me 0.8 moles because 20 decomposed. So at equilibrium, I'm going to have 0.8 moles. Let me just put X because I don't know what the X is. 8 of that was then left over, which is then my moles. Then I'm going to continue to say at equilibrium, it was still in a volume of 2 cubic decimeters. I'm going to divide this side by 2. Remember, the nice thing about it, it's already in cubic decimeters and not in cubic centimeters. So I'm just going to put it as it is. Divide this side by 2 as well. Let us see what I get. I'm going to have 0.8, divide that by 2. I'm going to get 0.4. So at equilibrium, I'm going to get 0.4. Remember, I have the X. Why do I keep the X? Because whatever X was, 20% decomposed, I still have 0.8 left at equilibrium. And remember, at equilibrium, we've got concentration. Concentration is mole per cubic decimeter. So let's see what I'm going to get on this side. It was in the same container. I'm going to have 0.4, divide that by 2. I'm going to get 0.2. So I'm going to get 0.2 on this side. Remember, the 0.2 that I've used was the 2 that had decomposed. Therefore, I'm going to keep the X on this side because I've used a ratio of this one, not knowing what X was. Concentration at equilibrium will have a SI unit of mole per cubic decimeter. Now it's just mathematics. First things first, I'm going to have my Kc. If you talk about your Kc, you talk about products. You have products over reactants. I'm going to do it the long way around so that everyone knows where I am. My products, remember, one thing you must remember, the number in front will become an exponent. So we use solid brackets to say concentration of NO2 to the exponent 2. And then on this side, I'm going to have N2O4 as my reactants. And this is then my value for the Kc. But I was told that the Kc is 0.16. Something to just stress on a little bit when you're doing this section here. When you have liquids and you have solids, you do not exclude them because the effective concentration of liquids and solids remains the same. Now I'm just going to plug it in. At the top, I'm going to have 0.04. I'm going to have 0.04. I'm going to have 0.2 rather, x, and that will then be squared. At the bottom, I'm going to have 0.4x. I'm just going to do mathematics. I'm just going to move and work up here as well. I'm going to have 0.16 on the side. I'm just going to help you with this because I am running out of time. If you put that in your calculator, you're going to get 0.04 x all over. I'm going to keep the one at the bottom as 0.4x. Remember, if it's multiplication between the two, you can then cancel 0.16. On this side, I'm going to get 0.1x. Divide both sides by 0.1. 0.1, this and this will cancel, and you should find your x value as 1.6 moles. This means 20% of the 6 moles was used, and we know that at equilibrium we had the 80% of this. So the unknown value of x was 1.6. What you needed to do is that you needed to just find out your mole ratios. There we are. This is then all that I have for today's show, which is for revision paper 2. All the best for tomorrow. Give it your all. Mwah. Tons of love coming from us.